So from the previous session said that the total angular momentum operator hat, well, operator squared, and the z component of the angular momentum operator L hat, those two operators, they commute. The commutator is 0, and therefore those two operators share, they have the same set of eigenfunctions, orthonormal eigenfunctions. So we'll use that property now. We'll write out two, as I was saying towards the end of the previous session, we will write out two eigenequations for the two different operators, L squared and Lz, with different eigenvalues, but with the same eigenfunctions. And we know they have the same eigenfunctions because the two operators commute. The two corresponding observables are compatible. Okay, so that's what's saying here. So here are the two eigenequations. This one is for the square of the total angular momentum, so L hat squared, and here's the eigenequation for the z component of the angular momentum hat. Right? Now let this lambda here be the allowed, or the eigenvalues, so the allowed values you can get if you measure the square of the total angular momentum, lambda. And here your second operator is the z component of L. The eigenvalues you let be mu, let's say, so lambda, mu, different. Right? These correspond to the allowed measured values of the absolute value of the angular momentum squared, right? And these mu here correspond to the allowed z component of the angular momentum. Right? Now notice here the eigenfunctions, we'll just call them psi, they're the same for both two, and that's because these two operators here commute. They are compatible. Right? The commutator is 0. So we can do this, and the fact that we can do that the eigenfunctions here and here for these two different operators, the fact that we can do this, use that they're the same set, is comes from the theory of the previous chapter. You know, we proved that earlier in the previous lecture. Right? Now, the reason why we chose the z component rather than the y or the x component is because in spherical polar coordinates, this operator here turns out to be very simple. In fact, it's just minus I h bar d bd phi. That's it. Whereas the Lx and the Ly were much more complicated. They had many more terms and were a function of two angles instead of one. So we chose this one because it's shorter, easier, and it's easier to work with. We can find solutions using this one rather than Lx or Ly more easily. Okay, and here's a case. Alright, so let's take this equation. So we choose the actual operator, the actual term, which is minus I h bar d bd phi. That's the operator for Lz. And we apply that operator to psi here. Here it is here. And we get mu psi. Now that's a very simple first order differential equation, right? So we can just write down the solution to psi, and it'll be some variable, some function, if you like, that's a function of the angle, because this is a partial derivative here, right, with respect to phi. So this function here is effectively a constant as far as phi is concerned. So it's just some function, call it, God, what is that, capital omega, theta, capital theta, I guess. So exponential I mu phi over h bar, right? You can get that almost from inspection, just looking at this. If you want to check it, you can differentiate it partially with respect to phi, and you'll get this equation back again, right? Now that's not an h. That's that's not an h inside. It's supposed to be just. Yeah, that's probably better. Yeah. It's just be a capital version of this, of theta. Right? Now, this psi function here, we need to impose certain constraints on it. As this theta angle, as we keep rotating by 2 pi, we get back to the same function. So this wave function here, if you like, every time we go, theta changes by 2 pi, in other words, a full rotation, we just get back to what we started with. We have this constraint, right? We want it to be single valued at a given angle. So if we add 2 pi to the angle, we're at the same angle, right? 2 pi corresponds to a full rotation. So we want this constraint to be true, right? So if we add 2 pi, we still have the same angle as the original. And that has implications. Like if you put for the phi here, if you put phi plus 2 pi and insist that this whole thing ends up the same, then that implies that this phi is of the following form. Now we did something like this quite a few lectures ago, so it's not new, and you could do it for homework if you want, again. And so this psi has to be something of this form. So it's capital theta, yeah, this thing, and this now becomes e to the im phi, and m is just an integer. It's just the whole set of integers, so 0, plus minus 1, plus minus 2, and where this m here is such that mu equals mh, and that comes out of this requirement. So you could do that for homework. Sorry, let me send you the picture. This requirement here, that mu is mh bar, comes from this requirement, right? And so your solution now for psi, which is the eigenfunction in these two eigenequations, is of this form, where m is just an integer. Okay? So this is yet another example where the imposing boundary conditions, in a sense, these constraints on the wave function, that they have to meet certain constraints, like the value is single valued. Every time you rotate your system by 2 pi radians, full rotation, then you should get back to the same values you started with, right? And that kind of boundary condition or constraint places constraints on the value of the quantity. In this case, on your wave function. All right. So we have already the solution in this form in terms of phi. Okay. These m's here are integers. Now let's try to solve for the other variable, because we have a function here that depends on phi, and we have another function here, capital theta, that depends on little theta, right? So we know what this is, the form it takes, but what's this one? So we need now to solve for capital theta, this variable, this function here. Alright, so how to do that? Well, we can use the other eigenequation, which we haven't used yet. So instead of having LZ hat, we've now got L hat squared. So we're